What if I told you that right now, somewhere in our galaxy, there's an object so dense that a single teaspoon of it would weigh 6 billion tons? And here's the part that will absolutely shatter everything you think you know about gravity. Inside this cosmic monster, gravity doesn't just pull things down. It creates something so bizarre, so fundamentally weird, that it breaks the very fabric of space and time itself. I'm talking about neutron stars, and what happens to gravity inside them is about to challenge everything you believe about physics. Picture this. Imagine taking the entire mass of our sun, that's 330,000 times heavier than Earth, and crushing it down into a sphere just 12 miles across. That's smaller than Manhattan. The gravitational forces at work here are so extreme that they literally turn matter inside out, create impossible substances, and bend reality in ways that sound like science fiction but are absolutely, terrifyingly real. But here's what will blow your mind. The gravity inside a neutron star doesn't just create the strongest gravitational field in the known universe after black holes. It creates layers of reality where the laws of physics stack on top of each other like a cosmic onion, each layer stranger than the last. We're talking about matter so dense that protons and electrons are crushed together to form particles that shouldn't exist, time that moves at different speeds depending on where you are, and gravitational forces so intense that they literally squeeze space itself. And the most shocking part? The gravity at the very center might be doing something that physics says is impossible, creating matter states that exist nowhere else in the universe, possibly even opening doorways to dimensions we can't imagine. Before we dive into this mind-bending journey, make sure to smash that like button. It helps more people discover these incredible cosmic mysteries. And subscribe if you want to explore more of the universe's most shocking secrets. Also, drop a comment and let me know, what country are you watching from, and what time is it there right now? I love seeing our global community of cosmic explorers. Now, let's begin our descent into one of the universe's most extreme environments, where gravity becomes something almost alien. To understand what happens to gravity inside a neutron star, we need to start with something familiar, then watch as reality gets progressively more twisted. Think of gravity like a cosmic sculptor, constantly molding and shaping matter. On Earth, this sculptor is gentle. It keeps your coffee in your cup and your feet on the ground. But as we venture into more extreme environments, this cosmic sculptor becomes increasingly aggressive, more violent, until it's literally tearing apart the very atoms that make up reality. Let's start our journey on familiar ground. Right now, you're experiencing Earth's gravity pulling you toward the center of our planet with an acceleration of about 9.8 meters per second squared. This seems perfectly normal to you because you've never known anything different. But here's your first mind-bending moment. You're actually in free fall right now. The only reason you're not plummeting toward Earth's core is because the ground is pushing back up against you. Gravity is constantly trying to pull you through the floor, and the electromagnetic forces between atoms in the floor are fighting back. You're caught in the middle of an invisible battle between fundamental forces. Now, what if I told you that as we venture deeper into space, toward more massive objects, this battle becomes more intense? On the surface of Jupiter, you'd weigh about 2.5 times more than you do on Earth. Your bones would strain, your heart would work overtime, and simple movements would become exhausting. But this is nothing compared to what's coming. Here's where things get interesting. In 1783, a brilliant geologist named John Michell proposed something that seemed impossible at the time. He calculated that if you could compress enough matter into a small enough space, gravity would become so strong that not even light could escape. He called these hypothetical objects dark stars. What Michell had unknowingly predicted were black holes, objects so gravitationally extreme that they literally tear holes in the fabric of space-time itself. But between normal stars and black holes exists something equally mind-blowing: neutron stars. These cosmic monsters were first theorized in 1934 by astronomers Walter Baade and Fritz Zwicky, just 2 years after the neutron itself was discovered. They proposed that when massive stars die in spectacular supernova explosions, the core could collapse so completely that it would create an entirely new form of matter made almost entirely of neutrons packed together at nuclear density. Think of it like this. Imagine you have a massive skyscraper, and suddenly all the empty space between floors disappears. The building doesn't just get shorter, it becomes so dense that what was once a 1,000-foot tall structure is now compressed into something the size of a marble, but with all the original mass still there. That's what happens during stellar collapse, but with an entire star. The numbers are almost incomprehensible. A neutron star packs roughly 1.4 times the mass of our Sun into a sphere only about 12 miles in diameter. To put this in perspective, if Earth were compressed to neutron star density, it would be about 600 feet across, roughly the size of a large city block. But it would still have all of Earth's mass, creating a gravitational field so intense that it would instantly be game over for everything we know about normal matter. Here's where your worldview starts to crack. At these densities, gravity becomes so strong that it fundamentally changes the rules of physics. We're not just talking about stronger gravity. We're talking about gravity so intense that it forces matter to exist in states that are literally impossible anywhere else in the universe. Atoms can't exist. Molecules become meaningless concepts. Even the neutrons themselves start to behave in ways that challenge our understanding of what matter actually is. But before we dive deeper into this cosmic madness, let me ask you this. What do you think happens to time itself when gravity becomes this extreme? Hold that thought, because what we discover next will completely reshape how you think about reality itself. The surface of a neutron star is where our journey into gravitational madness truly begins. And what we find here will challenge everything you think you know about the ground beneath your feet. Imagine stepping onto a surface where gravity is 200 billion times stronger than Earth's. Of course, you couldn't actually survive this. You'd be instantly crushed into a layer of atoms. So thin it would be invisible. But let's explore this impossible landscape through the lens of physics. The ground of a neutron star isn't really ground as we understand it. It's the most perfect crystal in the universe, made of atomic nuclei arranged in a lattice so precise it makes our best laboratory crystals look like random piles of rocks. This crystal crust is stronger than any material that could possibly exist on Earth, about 10 billion times stronger than steel. Yet despite this incredible strength, the surface is riddled with mountains and valleys that tell an incredible story about gravity's sculptural power. Here's what will blow your mind. These mountains are massive by Earth standards, some potentially several centimeters tall. I know that doesn't sound impressive, but remember, we're dealing with gravity 200 billion times stronger than Earth's. For a mountain to exist at all in this environment, it would have to be made of materials so incredibly strong that it defies imagination. These tiny peaks represent gravitational engineering on a scale that makes our largest Earth mountains look like gentle rolling hills. But the real magic happens in the crystal structure itself. The atomic nuclei in this crust are packed together in geometric patterns that exist nowhere else in the universe. Think of it like nature's most extreme architecture, where gravity has become the architect, forcing matter to arrange itself in ways that maximize density while still maintaining structural integrity. These aren't random arrangements. They're mathematical sculptures created by gravitational forces so intense they literally reorganize the fundamental building blocks of matter. And here's where things get even stranger. The surface temperature of a neutron star can reach over 1,000,000 degrees Celsius, making it hot enough to melt any substance known to science. Yet the crystal crust remains solid because the gravitational pressure is so immense that it prevents the nuclei from breaking apart their orderly arrangement. We're looking at matter that is simultaneously hotter than the core of the sun, yet more rigidly structured than the most perfect crystal. It's a state of matter that shouldn't be possible, yet gravity makes it inevitable. As we begin our descent beneath this crystalline surface, gravity starts to reveal its true artistic genius. Each step deeper takes us into increasingly bizarre realms where the normal rules of matter begin to break down. The deeper we go, the more densely packed the nuclei become, until something remarkable happens. The nuclei themselves start to change shape. Under the crushing weight of neutron star gravity, atomic nuclei that are normally spherical begin to deform into exotic shapes. Some become elongated like footballs, others flatten into pancakes, and some arrange themselves into bizarre geometric configurations that have never been observed in any laboratory on Earth. We're witnessing gravity, literally reshaping the fundamental components of matter, forcing them into configurations that exist only in these extreme environments. But here's the truly mind-bending part. As we continue deeper, we approach a boundary where even nuclei can't maintain their identity. The gravitational pressure becomes so intense that the barriers between individual nuclei start to break down. We're approaching what physicists call the neutron drip line, the point where neutrons begin to leak out of nuclei like water seeping through a dam. This is where gravity's true power begins to reveal itself. We're not just dealing with compressed matter anymore. We're witnessing the birth of entirely new forms of matter that exist nowhere else in the universe. And this is just the beginning. What happens next, as we cross into the outer core of the neutron star, will fundamentally challenge your understanding of what matter actually is. Crossing into the outer core of a neutron star is like stepping through a portal into an alien universe where the basic components of matter are completely different from anything in our everyday experience. Here, roughly a kilometer below the surface, gravity has become so overwhelmingly powerful that it has literally dissolved the concept of individual atomic nuclei. What we find instead is a sea of neutrons, pure neutron matter existing in a state that's impossible to replicate anywhere else in the cosmos. Think of it like this. Imagine you're at a crowded concert where people are packed so tightly together that individual boundaries disappear. Everyone becomes part of a single flowing crowd. That's what happens to matter in the outer core of a neutron star, except instead of people, we're talking about neutrons packed together at nuclear density, about 500 million tons per cubic centimeter. At this density, the neutrons aren't just close together. They're overlapping, creating a quantum fluid unlike anything that exists in normal matter. Here's what will absolutely blow your mind. This neutron fluid is a superfluid. That means it flows without any friction whatsoever. If you could somehow stir this neutron soup, it would continue spinning forever, never slowing down. But the truly bizarre part is that this superfluid doesn't just flow. It flows in quantized vortices, like microscopic tornadoes that are all exactly the same size and strength. Gravity has created a fluid so perfect, so alien, that it obeys quantum mechanical laws on a macroscopic scale. The discovery of neutron superfluidity was first predicted by physicist Lev Landau in 1941, but it wasn't until decades later that astronomers realized neutron stars were natural laboratories for observing these exotic quantum effects. When neutron stars occasionally glitch, suddenly speeding up their rotation slightly, we're witnessing these quantum vortices rearranging themselves in the superfluid core. It's like watching the quantum mechanics of individual particles playing out on the scale of an entire star. But the neutron superfluid is just the beginning. Mixed in with this sea of neutrons, we also find a small percentage of protons, typically about 5 to 10% of the total particles. And here's where things get even weirder. These protons also form a superfluid, but they're electrically charged. When charged particles flow without friction, they create perfect electrical currents that, like the neutron vortices, can persist forever. These superconducting protons generate magnetic fields so incredibly strong that they dwarf anything we can imagine. We're talking about magnetic fields trillions of times stronger than Earth's magnetic field, so strong that they would instantly be lethal to any form of life at distances of thousands of miles. These magnetic fields shape the behavior of matter in ways that seem almost supernatural, guiding charged particles along field lines and creating aurora-like phenomena on a cosmic scale. Here's your next mind-blown moment. The interaction between the neutron superfluid and the proton superconductor creates what physicists call flux tubes, essentially microscopic magnetic tornadoes threading through the stellar matter. Each flux tube carries exactly one quantum of magnetic flux, and they're all identical, like nature's most perfect mass production system. Gravity hasn't just created exotic matter. It's created exotic matter that organizes itself according to quantum mechanical principles scaled up to astronomical proportions. As we venture deeper into the outer core, the density continues to increase, and something even more remarkable begins to happen. The neutrons themselves start to pair up, forming what's called a neutron-Cooper pair, the same kind of pairing that creates superconductivity in normal metals, but now happening with neutrons in conditions billions of times more extreme than anything achievable in a laboratory. These neutron-Cooper pairs create regions of the core that are simultaneously superfluid and superconducting, leading to behavior that challenges our understanding of condensed matter physics. We're looking at matter that has no resistance to flow, no electrical resistance, and no way to lose energy through friction or heating. It's as if gravity has created the most perfect, most efficient form of matter possible. Matter that, once set in motion, continues that motion forever. But perhaps the most astonishing aspect of the outer core is how all these exotic properties emerge naturally from the crushing influence of gravity. We're not dealing with carefully controlled laboratory conditions or artificial constraints. Instead, gravity alone, through its relentless compression, has created conditions so extreme that matter is forced to adopt these quantum mechanical properties on a macroscopic scale. As we prepare to venture even deeper toward the mysterious inner core of the neutron star, remember this: everything we've seen so far, the crystal crust, the neutron superfluid, the magnetic flux tubes, exists because gravity has become so powerful that it forces matter to explore every possible way of existing. But what we're about to discover in the inner core pushes the boundaries of physics even further, into realms where our current understanding begins to break down entirely. As we descend toward the inner core of a neutron star, we're approaching the most mysterious region in the known universe outside of a black hole's event horizon. Here, at densities that exceed even nuclear density, gravity pushes matter beyond the boundaries of our current understanding, and possibly into realms of physics that we're only beginning to theorize about. What happens in this deep core isn't just exotic. It might represent entirely new forms of matter that exist nowhere else in the cosmos. The transition from the outer core to the inner core occurs when the density becomes so extreme that neutrons themselves can no longer maintain their individual identity. Think of it like this. Imagine you're compressing a sponge. At first, the air gets squeezed out, but the sponge material itself remains intact. Keep compressing, and eventually even the sponge material starts to break down. That's what happens to neutrons in the inner core. The crushing gravitational pressure becomes so intense that these fundamental particles begin to dissolve into their constituent parts, quarks and gluons. Here's what will blow your mind. Under these conditions, we might witness the birth of quark matter, a state where the strong nuclear force that normally confines quarks inside neutrons and protons completely breaks down. The quarks become deconfined, flowing freely in what physicists call a quark-gluon plasma. But this isn't the quark-gluon plasma we can create for microseconds in particle accelerators. This is stable quark matter, existing at densities and pressures that dwarf anything achievable in any laboratory. The theoretical physicist Edward Witten proposed in 1984 that this quark matter might actually be the most stable form of matter in the universe, more stable even than ordinary atomic nuclei. If Witten is correct, then the inner cores of neutron stars aren't just exotic laboratories for studying extreme physics. They might represent the ultimate destiny of all matter in the universe. This theory suggests that all the atoms making up planets, stars, and even our own bodies are actually metastable, temporarily stable, but ultimately destined to decay into quark matter given enough time and the right conditions. But the story gets even stranger. In this soup of liberated quarks and gluons, gravity might enable the creation of strange quark matter. Strange quarks are heavier, more exotic cousins of the up and down quarks that make up normal protons and neutrons. Under the crushing conditions in a neutron star's core, some theories suggest that strange quarks become energetically favorable, leading to the creation of particles like hyperons and kaons that exist only in the most extreme environments. Here's your next mind-blown moment. If strange quark matter is truly the ground state of all matter, as some theories suggest, then neutron stars with strange quark cores become incredibly dangerous cosmic bombs. A tiny piece of strange quark matter could theoretically convert any normal matter it touches into more strange quark matter in a chain reaction that could consume entire planets. It's like cosmic infection, matter converting other matter to a more stable but completely alien form. The possibility becomes even more mind-bending when we consider color superconductivity. Just as electrons can form Cooper pairs to create electrical superconductivity, quarks under extreme conditions can form their own exotic pairs, creating superconductivity based on the strong nuclear force rather than electromagnetism. This color superconducting quark matter would exhibit properties so bizarre that they challenge our fundamental understanding of condensed matter physics. Some theoretical models suggest that the inner core might contain pasta phases, regions where nuclear matter arranges itself into shapes resembling lasagna sheets, spaghetti strands, or gnocchi-like blobs. These aren't just cute names. They represent serious attempts to understand how matter behaves when nuclear forces and gravitational forces reach equilibrium at different density levels. Each pasta phase represents a different compromise between the attraction of nuclear forces and the crushing pressure of gravity. But perhaps the most speculative and mind-bending possibility is that the inner core might contain a phase transition to something even more exotic. Color glass condensate, or gluons, the particles that carry the strong nuclear force, themselves condense into a glass-like state. This would create matter with properties so alien that our current mathematics can barely describe it. Recent theoretical work by physicists like Mark Alford and Krishna Rajagopal has suggested that the phase diagram of matter under extreme conditions might be far richer and more complex than anyone previously imagined. They've proposed that the inner core might undergo multiple phase transitions, creating layers of different exotic matter states, each with its own unique properties and behaviors. Here's what should keep you awake at night. All of these exotic matter states exist because gravity has become so powerful that it forces particles to explore every possible way of arranging themselves. The inner core of a neutron star isn't just compressed normal matter. It's potentially a laboratory where matter experiments with forms of existence that are impossible anywhere else in the universe. And here's the truly unsettling part. We might never be able to study these matter states directly. The conditions required to create them are so extreme that they exist only in the hearts of neutron stars and possibly in the first microseconds after the Big Bang. We're dealing with physics that might forever remain theoretical, observable only through their gravitational effects on the behavior of neutron stars themselves. As we prepare to explore how these exotic matter states actually respond to and modify the gravitational field itself, remember this: everything we've discovered so far represents matter being forced by gravity to adopt increasingly alien forms. But what we're about to learn next will show you that these exotic matter states don't just passively respond to gravity. They actively modify and reshape the gravitational field in ways that turn our intuitions about space and time upside down. Now we reach the heart of our cosmic mystery. How does gravity actually behave when it encounters matter so exotic that it exists nowhere else in the universe? What we're about to explore will fundamentally challenge your understanding of gravity itself. Because inside a neutron star, gravity isn't just stronger. It becomes something qualitatively different, almost alien in its behavior. Let's start with a revelation that will reshape everything we've discussed so far. In Einstein's general relativity, gravity isn't actually a force pulling objects together. Instead, massive objects curve spacetime itself, and objects moving through that curved spacetime follow paths that we interpret as gravitational attraction. Think of it like this. Imagine a bowling ball placed on a stretched rubber sheet. The ball creates a depression, and if you roll marbles nearby, they curve toward the bowling ball, not because of any force, but because they're following the curved geometry of the sheet itself. Now, here's what will blow your mind. A neutron star creates a depression in spacetime, so extreme that it's almost like a vertical cliff. If our rubber sheet analogy held true, the neutron star would create a hole so deep and steep-sided that marbles rolling nearby would accelerate to incredible speeds before plunging over the edge. But the neutron star doesn't quite create a complete hole. It stops just short of becoming a black hole, creating instead the steepest possible gravitational well that still allows light to escape. The curvature of spacetime around and inside a neutron star is so extreme that it literally changes the geometry of space itself. Distances become stretched and compressed in ways that seem impossible. If you could somehow survive inside a neutron star and measure distances with a ruler, you'd find that space itself is so warped that your measurements would contradict everything you know about geometry. A straight line inside a neutron star would curve back on itself in ways that would make Euclidean geometry completely meaningless. Here's your next mind-blown moment. Time itself becomes variable inside a neutron star. Due to gravitational time dilation, time moves slower in stronger gravitational fields. At the surface of a neutron star, time runs about 30% slower than it does in empty space. But as we descend into the stellar core, this effect becomes even more extreme. Time in the inner core might run 50% or even 60% slower than time at the surface. What does this mean practically? If you could somehow place identical atomic clocks at different depths within a neutron star, they would tick at different rates. The deeper the clock, the slower it would run compared to clocks higher up. From the perspective of someone at the surface, processes in the core would appear to happen in slow motion. From the perspective of someone in the core, the surface world would appear to be racing by at high speed. But here's where things get truly bizarre. The exotic matter states we explored earlier don't just passively exist within this warped spacetime. They actively contribute to the warping. Each type of exotic matter, the neutron superfluid, the proton superconductor, the possible quark matter, affects spacetime curvature in its own unique way. The equation of state of matter, how pressure relates to density, directly determines how space and time are curved. The genius physicist Subramanian Chandrasekhar, working in the 1930s, first demonstrated that there are limits to how much matter can be compressed before gravity wins completely and creates a black hole. The Chandrasekhar limit showed that white dwarf stars can't exceed about 1.4 solar masses without collapsing further. Later, physicists like J. Robert Oppenheimer and George Volkoff extended this work to neutron stars, showing that they too have a maximum mass, probably around 2 to 3 solar masses, beyond which nothing can prevent complete gravitational collapse. This creates one of the most mind-bending aspects of neutron star physics. These objects exist right at the edge of what's possible in our universe. They represent the maximum density and gravitational field strength they can exist without creating a black hole. They're balanced on a knife's edge between exotic matter and the complete breakdown of spacetime itself. Recent observations by physicists like Feryal and Demetrius Saltis have shown that this knife's edge balance creates observable effects that we can detect from Earth. When matter falls onto a neutron star's surface, it follows trajectories through spacetime, so curved that light from the falling matter is bent and focused in ways that create characteristic signatures in X-ray emissions. We're literally watching spacetime geometry in action. Here's what should make you dizzy. The relationship between matter and spacetime in a neutron star creates a feedback loop that defies our everyday intuitions. The matter curves spacetime, but the curved spacetime also affects how the matter behaves. In regions where spacetime is most severely warped, the exotic matter states we discussed earlier become even more exotic. The quark matter in the core exists in a spacetime so curved that the usual rules for how quarks interact are modified by the geometry of space and time itself. This feedback between matter and spacetime creates what physicists call nonlinear effects. Changes in one aspect of the system cause changes in other aspects, which in turn cause further changes in the original aspect. It's like a cosmic hall of mirrors where cause and effect reflect back and forth, amplifying and modifying each other in ways that make the system incredibly complex and beautiful. The most extreme example of this feedback might occur near the neutron star's core, where some theoretical models suggest that the curvature of spacetime becomes so severe that it affects the fundamental constants of physics themselves. The strength of the nuclear force, the mass of particles, even the speed of light might become variable quantities that depend on position within the neutron star. As we prepare to explore the most mind-bending gravitational phenomena that occur in these extreme environments, remember this: we're not just looking at strong gravity. We're looking at gravity so extreme that it transforms the very nature of space, time, and matter. The neutron star exists in a regime where the familiar becomes alien, where the solid becomes fluid, where time becomes flexible, and where the geometry of reality itself becomes negotiable. What we're about to discover next will show you how these extreme gravitational conditions create phenomena so bizarre that they challenge our understanding of what's possible in our universe. Deep within the gravitational maelstrom of a neutron star, we encounter phenomena so extreme and bizarre that they seem to belong in the realm of science fiction rather than physics. These are the signatures of gravity pushed to its absolute limits, creating effects that not only challenge our understanding, but actively reshape the very fabric of reality around them. Let's begin with one of the most mind-bending consequences of extreme gravity: frame dragging. Einstein predicted that massive spinning objects would literally drag space-time around with them, like honey being stirred by a spoon. For most objects, this effect is incredibly subtle. Earth's rotation drags spacetime so slightly that we need incredibly precise experiments to detect it. But neutron stars spin incredibly fast, some rotating hundreds of times per second, and their immense gravitational fields amplify this frame-dragging effect until it becomes a dominant feature of the local spacetime geometry. Here's what will blow your mind. The spacetime around a rapidly spinning neutron star is so severely dragged that it becomes almost impossible for anything to remain stationary relative to a distant observer. If you could somehow hover near a spinning neutron star, the fabric of space and time itself would be flowing past you like a river, carrying you along whether you wanted to move or not. This creates regions where the normal concept of up and down becomes meaningless because space-time itself is rotating. The frame-dragging effect becomes so extreme that it creates what physicists call an ergosphere, a region where space-time is dragged around faster than the speed of light. Wait, that sounds impossible, right? Nothing can move faster than light. But here's the key insight. It's not matter moving faster than light. It's the geometry of space-time itself that's being dragged around. This creates a region where any object, no matter how it tries to resist, must rotate in the same direction as the neutron star. But frame dragging is just the beginning. The intense gravitational fields of neutron stars create what are called gravitational waves, ripples in spacetime, itself that propagate outward at the speed of light. When neutron stars have slight imperfections in their shape, remember those tiny mountains we discussed earlier, their rotation creates oscillating gravitational fields that literally shake the fabric of spacetime. The Laser Interferometer Gravitational Wave Observatory, LIGO, which first detected gravitational waves in 2015, has opened up an entirely new way of studying neutron stars. When two neutron stars spiral into each other and merge, they create gravitational waves so powerful that they can be detected from billions of light years away. But here's the truly amazing part. These gravitational waves carry information about the properties of matter under conditions so extreme that they exist nowhere else in the accessible universe. Physicists like Kip Thorne and Rainer Weiss, who won the Nobel Prize for their work on gravitational wave detection, realized that these ripples in spacetime are like cosmic messengers, carrying information about the equation of state of matter at nuclear densities and beyond. By analyzing the gravitational wave signatures from neutron star mergers, we can actually probe the physics of exotic matter states that we can never hope to create or study directly in laboratories. Here's your next mind-blown moment. The gravitational waves from neutron star mergers have already revealed that these objects contain matter states that are softer or stiffer than our best theoretical predictions. This means that the actual behavior of matter under extreme conditions differs from what our current theories suggest, forcing us to revise our understanding of fundamental physics. We're literally using the fabric of spacetime as a laboratory instrument to study matter physics. But perhaps the most mind-bending gravitational phenomenon in neutron stars is the creation of closed time-like curves, paths through spacetime that loop back on themselves temporally. In the most extreme theoretical models of rapidly spinning neutron stars, the dragging of spacetime becomes so severe that it might be possible for cause and effect to become scrambled. An event could theoretically influence its own past, creating paradoxes that challenge our understanding of causality itself. Now, before you start planning time travel adventures, these closed time-like curves, if they exist at all, would be microscopic and would exist only in the most extreme regions near the neutron star surface. They represent the absolute limit of what's possible in our universe without crossing over into black hole territory. But their mere theoretical possibility shows just how profoundly extreme gravity can warp the normal flow of time. The gravitational lensing effects around neutron stars create another class of mind-bending phenomena. Light from the backside of a neutron star can be bent around the star's edge and become visible to observers on the front side. This means that if you could somehow observe a neutron star up close, you would see more than half of its surface simultaneously, the front hemisphere directly, and portions of the back hemisphere through gravitationally lensed light paths. This lensing effect becomes so extreme that it creates multiple images of objects behind the neutron star. A single star located directly behind a neutron star would appear as a ring of light surrounding the neutron star. A gravitational version of the optical lensing effects you might see in a funhouse mirror, but created by the curvature of spacetime itself rather than curved glass. Recent theoretical work by physicists like Farial Zeil has shown that the gravitational lensing signature of neutron stars can be used as a probe of their internal structure. The exact way that light bends around a neutron star depends on the mass distribution within the star, which in turn depends on the exotic matter states in the core. By measuring these lensing effects precisely, we might be able to determine whether the core contains normal neutron matter, strange quark matter, or even more exotic states. But perhaps the most profound consequence of extreme gravity in neutron stars is how it affects the fundamental constants of physics themselves. In the most extreme theoretical models, the gravitational field becomes so strong that it modifies the effective strength of other fundamental forces. The electromagnetic force, the weak nuclear force, even the rate of radioactive decay might become functions of position within the neutron star. This creates a universe within a universe, a region of space where the laws of physics themselves are different from what we observe in the rest of the cosmos. If this is true, then neutron stars aren't just objects existing within our universe. They're regions where our universe transitions into something alien, governed by modified physical laws that we're only beginning to understand. As we prepare to explore how all of these extreme gravitational effects connect to your daily life and worldview, remember this: the phenomena we've explored represent gravity pushed to its absolute limits. They show us what happens when one of the fundamental forces of nature becomes so extreme that it reshapes space, time, matter, and potentially even the laws of physics themselves. What we're about to discover next will connect these cosmic extremes to your personal experience and show you why understanding neutron star gravity might be one of the most important intellectual adventures you can undertake. You might be wondering, why should I care about the bizarre gravitational physics happening inside objects that are hundreds or thousands of light years away? What does any of this have to do with my daily life, my understanding of myself, or my place in the universe? The answer is about to fundamentally reshape how you see reality, because the extreme gravitational effects in neutron stars reveal profound truths about the nature of existence that touch every aspect of your world. Let's start with something that should make you pause and think. The atoms that make up your body were forged in the nuclear furnaces of massive stars, and when those stars died in supernova explosions, they created the very neutron stars we've been exploring. But here's what will blow your mind. The gravitational processes we've discussed don't just create neutron stars. They also create and disperse the heavy elements that make life possible. When neutron stars merge, the extreme gravitational and nuclear forces create a cosmic alchemy that produces gold, platinum, uranium, and other elements that can't be made any other way in the universe. The gold in your jewelry, the platinum in your electronics, the iodine in your thyroid, these elements were literally forged in neutron star collisions, created by the same gravitational extremes we've been exploring. You are carrying within your body the products of some of the most violent and exotic gravitational events in the cosmic history. But the connection runs much deeper than just elemental composition. The gravitational physics of neutron stars reveals something profound about the nature of reality itself, something that should change how you think about space, time, and your own existence. Remember how we discussed that time runs slower in stronger gravitational fields? This isn't just an abstract theoretical concept. It's a fundamental feature of the universe that affects you right now. Here's your next mind-blown moment. You experience gravitational time dilation every day. Time runs slightly slower at your feet than at your head because your feet are slightly closer to Earth's center and therefore in a slightly stronger gravitational field. The difference is minuscule. We're talking about nanoseconds over a lifetime, but it's real and measurable. GPS satellites must account for gravitational time dilation to maintain accuracy. The universe you live in is one where time is not absolute, where your elevation above sea level literally affects how quickly you age relative to someone else. This reveals something profound. Your intuitive understanding of time as a universal constant flowing at the same rate everywhere is wrong. Time is flexible, variable, dependent on gravity and motion. The extreme examples we see in neutron stars show us the outer limits of this flexibility, but the same physics applies to you right now as you read these words. The exotic matter states in neutron stars also reveal something crucial about the material world around you. Every solid object you touch, your phone, your chair, the walls around you, is held together by electromagnetic forces between atoms. But these atoms are mostly empty space. If an atom were the size of a football stadium, the nucleus would be smaller than a marble at the center, and the electrons would be tiny specks orbiting in the outer seats. Think about this. You've never actually touched anything in your entire life. When you press your finger against a table, the electromagnetic forces between electrons in your finger and electrons in the table create a repulsive force that stops your finger from passing through. You're experiencing the illusion of solidity created by invisible force fields. The solid matter you interact with every day is mostly nothingness held together by forces. Now, the neutron stars we've explored show us what happens when gravity becomes so strong that it overwhelms these electromagnetic forces and crushes the empty space out of matter entirely. In doing so, they reveal that the solidity you experience, the resistance of objects to your touch, the apparent permanence of the physical world, is actually a delicate balance of forces that exists only under the relatively gentle gravitational conditions we experience on Earth. This should profoundly shift your perspective on physical reality. The matter that seems so solid and permanent to you is actually in a temporary, metastable state that exists only because gravity hasn't yet become strong enough to compress it into more exotic forms. Under different conditions, the conditions we find in neutron stars, this same matter would become superfluid, superconducting, or even dissolve into free quarks. Here's what should keep you awake at night. The universe is filled with regions where matter exists in states so alien that they challenge our basic concepts of what stuff actually is. The familiar properties of matter, solidity, distinct boundaries between objects, the separation between different materials, these are all features of a low-energy, low-density regime that happens to be where we evolved. They're not fundamental truths about reality. They're just the particular way matter behaves under the specific conditions we're used to. But the personal implications go even deeper. The study of neutron star gravity has revealed that the universe operates according to principles that are far stranger and more flexible than our everyday experience suggests. The same equations that describe the exotic matter in neutron star cores also govern the behavior of matter and energy throughout the cosmos, including the matter and energy that makes up your brain as it processes these ideas right now. Your consciousness, whatever that actually is, depends on electrochemical processes in neurons that are governed by the same fundamental forces we've been exploring. The electromagnetic forces that create nerve impulses, the quantum mechanical effects that might play a role in consciousness, the gravitational fields that shape the large-scale structure of your brain, all of these operate according to the same physics that creates neutron superfluids and quark matter. This creates a profound connection between the most exotic cosmic phenomena and your inner mental life. When you think, you're manipulating patterns of matter and energy according to the same fundamental laws that govern neutron stars. The difference is only one of scale and energy density, not of fundamental physics. The gravitational time dilation effects in neutron stars also reveal something crucial about memory and identity. If time itself is flexible and dependent on gravitational conditions, then your personal timeline, your memories, your sense of duration, your experience of aging, is also tied to your gravitational environment. Your memories of yesterday occurred in a gravitational field, and if that field had been different, those memories would have been formed at a different rate relative to the rest of the universe. Here's your next mind-blown moment. Imagine if you had grown up in a slightly stronger gravitational field, say, on a planet twice as massive as Earth. Not only would you be physically stronger to cope with the increased gravity, but your entire life timeline would be running slightly slower relative to someone who grew up on Earth. Your thoughts, your experiences, your entire conscious timeline would be stretched compared to an Earth dweller. You would literally be living your life at a different temporal rate. This isn't science fiction speculation. It's a direct consequence of the gravitational physics we've explored. The extreme cases in neutron stars show us the outer limits of these effects, but the same principles apply everywhere. Your consciousness exists within the flow of time, and that flow is determined by the gravitational environment you inhabit. The frame-dragging effects around spinning neutron stars also illuminate something profound about causality and free will. If space-time itself can be dragged around by massive spinning objects, then the arena in which cause and effect play out, the stage on which your decisions and actions occur, is not a fixed backdrop, but a dynamic, flowing medium that can be influenced by matter and energy. This raises deep questions. If the geometry of space-time affects the paths that information and influence can take between events, does this change the nature of causality itself? When you make a decision, that decision propagates through space-time according to the curvature created by all the mass and energy in your vicinity. The gravitational field of Earth, the Sun, even distant galaxies all contribute to shaping the space-time through which the consequences of your choices propagate. The exotic matter states in neutron stars show us that the same fundamental ingredients, quarks, electrons, photons, can be arranged in radically different ways depending on the conditions they encounter. This has profound implications for how you think about your own identity and potential. The atoms that make up your body could, under different conditions, form exotic matter states with completely different properties. You are a particular arrangement of matter and energy that exists only under specific conditions. Change those conditions dramatically, increase the density, alter the temperature, modify the gravitational field, and the same fundamental components would reorganize into something completely different. Your identity as a human being depends on the delicate balance of forces that allows complex chemistry and biology to exist. But here's the empowering part. Understanding these cosmic connections doesn't diminish your significance. It reveals how extraordinary your existence actually is. You are a temporary but magnificent arrangement of matter and energy that arose from the same cosmic processes that create neutron stars. The same physics that governs the most extreme objects in the universe also enables the complex patterns of organization that make your thoughts, feelings, and experiences possible. The gravitational waves from neutron star mergers that we can now detect with LIGO carry information across billions of light years of space and time. But they also carry a message about the fundamental interconnectedness of all things in the universe. The ripples in space-time created by cosmic events billions of years ago are still propagating through the universe, subtly affecting the geometry of space and time around you right now. You exist within a universe where every massive object, every star, planet, and galaxy contributes to the overall curvature of space-time. Your own mass, tiny as it is on cosmic scales, also contributes to this curvature. You are both influenced by and influencing the geometry of the universe itself. As we prepare to explore the cutting-edge discoveries that are revolutionizing our understanding of neutron star gravity, remember this. These aren't just abstract cosmic phenomena happening in distant corners of the universe. They're revelations about the fundamental nature of the reality you inhabit every day. The extreme conditions in neutron stars serve as cosmic laboratories that reveal truths about space, time, matter, and causality that apply throughout the universe, including in your own backyard, in your own body, and in your own consciousness. What we're about to discover next represents the bleeding edge of human knowledge. Observations and theories so new that they're still reshaping our understanding of what's possible in the cosmos. The last decade has witnessed a revolution in our understanding of neutron star gravity, driven by observations so precise and discoveries so unexpected that they're forcing physicists to rewrite textbooks and reconsider fundamental assumptions about the nature of matter and space-time. What we're about to explore represents the absolute cutting edge of human knowledge, discoveries so recent that their full implications are still being debated in physics journals around the world. The revolution began on August 17, 2017, with an event that will be remembered as a watershed moment in astrophysics. The LIGO and Virgo gravitational wave detectors simultaneously recorded ripples in spacetime from two neutron stars spiraling into each other 130 million light-years away. But this wasn't just another gravitational wave detection. Within seconds, telescopes around the world were pointed at the same region of sky, capturing light from the cosmic collision in unprecedented detail. Here's what blew everyone's mind. The gravitational wave signal contained information about the internal structure of neutron stars that had never been accessible before. As the two neutron stars spiraled closer together, the gravitational waves they emitted carried signatures of how easily the stars deformed under each other's gravitational influence. This tidal deformability depends directly on the equation of state of matter and nuclear densities, exactly the exotic physics we've been exploring. The results were shocking. The data revealed that neutron star matter is softer than many theoretical models predicted, meaning it's more easily compressed and deformed than expected. This suggests that the exotic matter states in neutron star cores might be even stranger than we thought, possibly indicating the presence of previously unknown particles or new phases of matter that exist nowhere else in the universe. But the gravitational wave detection was just the beginning. The optical observations of this supernova explosion revealed something that fundamentally changed our understanding of cosmic chemistry. The collision produced a fireball that synthesized massive amounts of heavy elements. We're talking about Earth masses of gold and platinum created in a matter of seconds. The light from this explosion showed spectral signatures of heavy element formation that confirmed decades of theoretical predictions about how the universe creates its most precious metals. Here's your next mind-blown moment. This single event produced more gold than all the stars in the observable universe had created through normal stellar fusion over billions of years. The extreme gravitational conditions during the merger created temperatures and pressures so intense that they enabled nuclear processes impossible under any other circumstances. You're looking at gravitational engineering on a cosmic scale, where the curvature of spacetime itself becomes a tool for creating new forms of matter. Recent work by physicist Anna Watts and her collaborators at the University of Amsterdam has pushed these discoveries even further. Using NASA's Neutron Star Interior Composition Explorer, NICER, mounted on the International Space Station, they've been able to measure the precise shape and size of individual neutron stars by analyzing the X-ray emissions from their surfaces. What they've found challenges everything we thought we knew about neutron star structure. The measurements reveal that neutron stars are remarkably spherical, far more spherical than expected based on their rapid rotation. Some neutron stars spin hundreds of times per second, which should cause them to bulge significantly at their equators due to centrifugal forces. But the observed shapes suggest that the interior structure is far more rigid than our models predict, possibly indicating exotic matter phases that have mechanical properties unlike anything we can imagine. Even more mind-bending are the recent discoveries about neutron star magnetic fields. The magnetar SGR 1745 to 2900, discovered near the center of our galaxy, has a magnetic field strength of about 100 trillion times stronger than Earth's field. But recent theoretical work by physicist Dmitry Uzdensky suggests that the strongest magnetar fields might approach the critical field strength where quantum electrodynamics, the theory governing light and matter, breaks down completely. At these field strengths, the vacuum of empty space itself begins to behave differently. Virtual particle pairs that normally exist for infinitesimally brief moments become real, permanent particles. The magnetic field becomes so strong that it literally tears electron-positron pairs out of the quantum vacuum, filling space with exotic plasma that behaves according to rules we're only beginning to understand. Here's what should make your head spin. These magnetic fields are so intense that they change the atomic structure of matter. In the strongest magnetar fields, atoms become elongated into needle-like shapes, with electron orbitals stretched into cylinders rather than the familiar spherical or dumbbell shapes you learned about in chemistry. The periodic table of elements becomes meaningless because the same atoms behave completely differently depending on their orientation relative to the magnetic field. Recent discoveries about fast radio bursts, FRBs, have opened another window into neutron star physics. These are millisecond duration flashes of radio waves so bright that they can be detected from billions of light years away. In 2020, astronomers finally traced one of these bursts to a magnetar in our own galaxy, confirming that at least some FRBs are produced by neutron stars. But here's the truly mind-bending part. The energy released in a single fast radio burst from a magnetar can exceed the total energy output of our Sun over several days, all released in less than a millisecond. The physics required to generate such intense, brief energy releases involves gravitational and magnetic field interactions so extreme that our current theories can barely explain them. Theoretical physicist Bing Zhang at the University of Nevada has proposed that these bursts might involve starquakes, sudden rearrangements of the neutron star's crust that release gravitational potential energy built up over thousands of years in a single catastrophic event. But the energy scales involved suggest that these aren't just rearrangements of the surface. They might involve phase transitions in the exotic matter of the core itself. Perhaps the most revolutionary recent discovery involves pulsar timing arrays, networks of pulsars monitored with incredible precision to detect gravitational waves. These natural cosmic clocks are so regular that they can detect gravitational wave frequencies that LIGO can't observe. Recent results suggest that the universe is filled with a background of gravitational waves, possibly created by countless neutron star mergers throughout cosmic history. But here's the truly staggering implication. This gravitational wave background means that space-time around us is constantly rippling with the echoes of neutron star collisions from across the universe and throughout cosmic time. You are literally immersed in a sea of gravitational waves carrying information about exotic matter physics from every corner of the cosmos. The most recent theoretical breakthroughs come from computer simulations that can now model neutron star mergers in unprecedented detail. Work by physicists like David Radis at Pennsylvania State University has revealed that the gravitational wave signatures from these mergers encode information about phase transitions between different exotic matter states within the colliding stars. These simulations suggest that during a merger, the cores of the neutron stars might undergo rapid phase transitions from neutron matter to quark matter and back again as the density and temperature fluctuate wildly. Each phase transition would create characteristic signatures in the gravitational wave signal, essentially giving us a real-time readout of exotic matter physics under the most extreme conditions possible. The implications are staggering. We might be able to use gravitational wave astronomy to study physics that's impossible to access any other way. The universe has provided us with natural laboratories operating at energy scales and densities that we can never hope to achieve artificially. And the gravitational waves they produce are like cosmic radio broadcasts telling us about the fundamental nature of matter and space-time. But perhaps the most mind-blowing recent development is the possibility that neutron stars might be even more exotic than we ever imagined. Some cutting-edge theoretical models suggest that the most massive neutron stars might contain mirror matter, hypothetical particles that interact only through gravity and the weak nuclear force. If mirror matter exists in neutron star cores, it would be completely invisible to normal matter except through its gravitational effects. This would mean that neutron stars aren't just made of exotic normal matter. They might contain entire shadow populations of particles that exist in a parallel invisible sector of physics. The gravitational fields we observe would be the combined effect of both normal exotic matter and mirror exotic matter, creating complexity beyond anything we've previously considered. As we prepare to explore what all of these cutting-edge discoveries mean for the future of physics and our understanding of the universe, remember this: every observation, every theoretical breakthrough, every new discovery reveals that reality is far stranger and more wonderful than our wildest imaginations. The neutron stars we've been exploring aren't just cosmic curiosities. They're cosmic laboratories, revealing fundamental truths about the nature of existence itself. What we're about to discover next will show you how these revelations point toward a future where our understanding of gravity, matter, and space-time might be completely transformed. As we stand at the frontier of neutron star research, we're witnessing the birth of entirely new fields of physics that will fundamentally transform our understanding of reality over the coming decades. The discoveries we've explored aren't just adding details to our existing theories. They're revealing that our current understanding is just the tip of an iceberg of cosmic complexity that extends far deeper than anyone imagined. The future of neutron star gravity research promises to unlock secrets that will revolutionize technology, reshape our understanding of fundamental physics, and possibly reveal new forms of matter and energy that could transform human civilization. What we're about to explore represents the cutting edge of human knowledge, pushing into territories that seem more like science fiction than science. Yet they're grounded in rigorous observations and theoretical work happening right now. Let's start with the most immediate frontier, the next generation of gravitational wave detectors coming online over the next decade. The Cosmic Explorer and Einstein Telescope projects will be so sensitive that they'll detect neutron star mergers from across the entire observable universe. But here's what will blow your mind. These detectors won't just observe more events. They'll be able to probe the internal structure of neutron stars with unprecedented precision. Think of it like this. Current gravitational wave detectors are like listening to a symphony from outside a concert hall. You can hear the music, but you miss the subtle details. The next generation will be like having perfect hearing from the best seat in the house, able to distinguish individual instruments and hear every nuance of the performance. Applied to neutron stars, this means we'll be able to detect phase transitions between different exotic matter states in real time as stars merge. Here's your next mind-blown moment. These future detectors might be sensitive enough to detect gravitational waves from individual neutron starquakes, sudden rearrangements of the stellar crust that release energy equivalent to millions of hydrogen bombs. Each starquake would provide a direct probe for the mechanical properties of matter at nuclear densities, essentially using the neutron star as a cosmic laboratory for materials science under impossible conditions. But the implications extend far beyond pure science. The exotic matter physics we're discovering in neutron stars might hold keys to technological revolutions that seem impossible today. The superconducting and superfluid properties of neutron star matter, if we could somehow replicate them under laboratory conditions, would enable technologies that seem magical by current standards. Imagine materials that conduct electricity with absolutely zero resistance at room temperature, or fluids that flow without any friction whatsoever. These aren't just incremental improvements to existing technology. They would represent fundamental breakthroughs that could transform energy storage, transportation, computing, and manufacturing in ways we can barely imagine. Recent theoretical work by physicist Gordon Baim at the University of Illinois suggests that some of the exotic matter phases in neutron stars might be stable under much less extreme conditions than previously thought. If this is true, we might eventually be able to create tiny amounts of neutron star matter in specially designed magnetic confinement systems, essentially creating microscopic neutron stars in Earth-based laboratories. The possibilities are staggering. Neutron star matter has an energy density millions of times greater than any chemical fuel. A pinhead-sized amount would contain more energy than a nuclear power plant produces in a year. If we could harness this energy density safely, it would revolutionize space travel, making interstellar journeys practical for the first time in human history. But the future implications go even deeper than technology. The study of neutron star gravity is revealing that space-time itself might be far more malleable and complex than Einstein's general relativity suggests. Some cutting-edge theories propose that the extreme conditions in neutron star cores might create space-time defects, regions where the normal geometry of space and time breaks down and is replaced by something entirely alien. Physicist Lee Smolin at the Perimeter Institute has suggested that these space-time defects might serve as natural laboratories for testing theories of quantum gravity, the long-sought unification of quantum mechanics and general relativity. The most extreme neutron stars might be probing physics at the Planck scale, where space and time themselves become quantized, existing in discrete units rather than as continuous fields. If this is true, then neutron stars aren't just exotic objects within our universe. They're windows into the fundamental quantum structure of reality itself. The gravitational wave signals from neutron star mergers might carry information about the quantum nature of spacetime, encoded in subtle signatures that we're only beginning to learn how to interpret. The implications for our understanding of consciousness and intelligence are equally profound. If spacetime itself has quantum properties that become apparent under extreme conditions, and if consciousness somehow depends on quantum mechanical processes in the brain, then understanding neutron star physics might provide insights into the nature of consciousness itself. Here's what should make you dizzy. Some theories suggest that the quantum vacuum, the apparently empty space that fills the universe, might actually be teeming with virtual particles and quantum fields that become real under the extreme conditions found in neutron stars. This would mean that empty space is actually a complex, dynamic medium filled with potential matter and energy that becomes manifest only under the most extreme gravitational conditions. The future of neutron star research also promises to revolutionize our understanding of the fundamental constants of physics. Recent theoretical work suggests that some of the exotic matter phases in neutron star cores might exist in regions where the effective strength of fundamental forces, the electromagnetic force, the strong nuclear force, even the gravitational force itself, are different from their values in normal space. This opens up mind-bending possibilities. If the fundamental constants of physics can vary depending on local conditions, then the laws of physics themselves might be more flexible than we've assumed. The universe might contain regions where chemistry works differently, where atoms have different properties, where the very rules governing matter and energy are modified by extreme gravitational fields. Physicist John Barrow at Cambridge University has suggested that neutron stars might serve as natural laboratories for testing whether the fundamental constants have changed over cosmic time. If the properties of neutron star matter depend on the precise values of fundamental constants, then observations of neutron stars at different distances, and therefore different cosmic epochs, might reveal whether these constants have evolved as the universe has aged. The search for strange quark matter in neutron star cores represents another frontier with revolutionary implications. If strange quark matter is indeed the most stable form of matter in the universe, as some theories suggest, then every atom in your body, every planet, every star is actually metastable, temporarily stable, but ultimately destined to decay into a more stable form. This would mean that the familiar matter making up our world exists in a kind of cosmic metastable equilibrium, like a ball balanced on a hilltop that could roll down to a lower energy state if given the right push. Neutron stars might be the cosmic laboratories where we first observe this phase transition, providing a preview of the ultimate fate of all matter in the universe. But perhaps the most revolutionary possibility is that neutron star research might lead us to discover entirely new fundamental forces or particles. The discrepancies between theoretical predictions and observational data that we've discussed suggest that our current understanding of matter and gravity is incomplete. Some physicists have proposed that neutron stars might interact with dark matter in ways that modify their structure and evolution. If dark matter particles can be captured and concentrated in neutron star cores, they might create exotic hybrid objects that are part normal matter, part dark matter, cosmic laboratories for studying the mysterious substance that makes up 85% of all matter in the universe. The detection of such dark matter effects in neutron stars would represent one of the most significant discoveries in the history of physics, finally providing direct evidence for the nature of dark matter and potentially revealing entirely new sectors of physics beyond the standard model. As we prepare to explore how all of these discoveries and future possibilities connect to the biggest questions about existence itself, remember this: we're living through a golden age of discovery, where our understanding of the most extreme physics in the universe is expanding at an unprecedented rate. The neutron stars we've been exploring aren't just distant cosmic objects. They're cosmic laboratories, revealing fundamental truths about the nature of reality that will reshape human knowledge for generations to come. What we're about to discover next will connect all of these cosmic revelations to the deepest questions about existence, consciousness, and our place in the universe. As we reach the climax of our journey through the gravitational extremes of neutron stars, it's time to step back and grapple with the most profound implications of everything we've discovered. These aren't just abstract physics concepts happening in distant corners of the universe. They're revelations about the fundamental nature of reality that should fundamentally reshape how you think about existence, consciousness, and your place in the cosmic story. Let me start with a question that should keep you awake at night. If matter can exist in such radically different states, depending on the gravitational environment, from the familiar atoms in your body to the exotic superfluids and quark matter in neutron star cores, what does this tell us about the nature of identity and permanence? You think of yourself as a stable, continuous entity, but you're actually a temporary arrangement of particles that could, under different conditions, reorganize into completely alien forms. Here's what should blow your mind. The atoms that make up your body right now have existed for billions of years, cycling through countless different forms, inside stars, scattered through interstellar space, incorporated into planets, and now temporarily assembled into the complex pattern that is you. These same atoms could theoretically exist as exotic matter in a neutron star, where they would lose all their familiar properties and become part of a nuclear superfluid. This reveals something profound about the relationship between form and identity. What makes you you isn't the specific atoms you're made of. Those are constantly being replaced through metabolism anyway. Instead, your identity emerges from the pattern, the information, the specific way those atoms are arranged and interact with each other. You are a temporary but magnificent pattern imposed on matter that is itself temporary and ever-changing. The extreme gravitational time dilation we've explored in neutron stars illuminates something equally profound about the nature of consciousness and experience. Your subjective experience of time, your memories, your sense of duration, your feeling of continuity from moment to moment, depends on the rate at which physical processes occur in your brain. But we've seen that this rate can vary depending on gravitational conditions. Think about this. If you could somehow exist in the gravitational field of a neutron star, ignoring the obvious fact that you'd be instantly killed, your thoughts would occur more slowly relative to an outside observer, but they would feel perfectly normal to you. Your subjective experience of time would be unchanged, but you'd be living your mental life at a different rate than someone in a weaker gravitational field. This suggests that consciousness itself is intimately tied to the gravitational structure of space-time. Your thoughts, memories, and experiences don't occur in some abstract mental realm. They emerge from physical processes that are governed by the same gravitational physics that creates neutron superfluids and warps space-time around massive objects. Here's your next mind-blown moment. The gravitational waves from neutron star mergers that we can now detect carry information that has traveled across billions of light years and billions of years of time. These ripples in space-time connect us directly to cosmic events that occurred when the universe was young, carrying messages about the fundamental properties of matter and energy under conditions that existed nowhere else at those times. When you contemplate these discoveries, you're engaging in a process that spans cosmic scales of space and time. Your brain, made of atoms forged in stellar cores and dispersed by supernova explosions, is processing information about gravitational physics that governs the largest structures in the universe. The same fundamental forces that shape galaxy clusters and bend light around neutron stars also guide the electrochemical processes that create your thoughts and awareness. This creates a profound sense of cosmic connection that should transform how you see yourself in relation to the universe. You're not a separate observer looking at cosmic phenomena from the outside. You're an integral part of the cosmic story, a local concentration of matter and energy that has achieved self-awareness and is now contemplating its own origins and nature. The exotic matter states in neutron stars also reveal something crucial about the relationship between possibility and actuality in our universe. The same fundamental laws of physics that allow you to exist also allow for the creation of matter so exotic that it challenges our basic concepts of what stuff can be. The universe is far stranger and more creative than our everyday experience suggests. This should inspire a sense of humility about human knowledge and a sense of wonder about the vast unexplored territories of possibility that surround us. We've discovered that matter can exist as superfluid neutrons, as quark-gluon plasmas, as crystalline nuclear lattice, and possibly in even more exotic forms that we haven't yet imagined. If matter, the seemingly solid familiar stuff of our everyday world, can be this strange and flexible, what other aspects of reality might be far different from our assumptions? The frame-dragging effects around rotating neutron stars reveal that even space-time itself, the arena in which all events occur, is dynamic and malleable. The stage on which the drama of existence plays out isn't a fixed backdrop, but a flowing, changing medium that participates in the events it contains. This has profound implications for how you think about causality and free will. Your decisions and actions propagate through a space-time that has been shaped by every massive object in the universe. The consequences of your choices follow paths through space-time that have been determined by the collective gravitational influence of countless stars, planets, and galaxies. You're not making decisions in isolation. You're making them within a cosmic context that connects with everything that has ever existed. The gravitational field that guides the propagation of your choices is the cumulative result of every mass that has ever existed in the universe's history. But rather than diminishing your significance, this cosmic connection should enhance your sense of purpose and wonder. You are a conscious, thinking part of a universe that has evolved the capacity to understand itself. The atoms in your brain are engaging with concepts about neutron star, physics that reveal the deep mathematical structure underlying all of reality. The universe has spent 13.8 billion years evolving from simple hydrogen and helium into the complex structures that make galaxies, stars, planets, and ultimately, thinking beings like yourself. You represent the universe becoming self-aware, developing the capacity to study its own most extreme and beautiful phenomena. The gravitational waves from neutron star mergers carry information across cosmic distances, but they're meaningless without conscious beings to detect and interpret them. You are part of the universe's growing capacity to know itself, to understand its own deep principles, to appreciate its own beauty and complexity. Every time you contemplate the physics of neutron stars, you're participating in the most profound process possible, the universe using part of itself, your brain, to understand other parts of itself, neutron stars, according to principles, physical laws, that apply throughout itself. You are both the universe's student and its teacher, its observer and its subject, its question and its answer. The exotic matter in neutron stars exists in states that challenge our understanding, but your own existence as a conscious, thinking being is equally remarkable and equally mysterious. The complex chemistry that creates your thoughts and experiences is just as impressive as the exotic physics that creates neutron superfluids. It's just operating under different conditions. As we prepare for our final revelations, about what neutron star gravity teaches us about the ultimate nature of reality. Remember this. You're not just learning about distant cosmic objects. You're discovering fundamental truths about the universe that created you, that contains you, and that you are an integral part of. The most extreme gravitational phenomena in the cosmos are connected to the most intimate aspects of your own existence. What we're about to explore next will bring together all of these cosmic revelations and show you how the study of neutron star gravity points toward the deepest mysteries of existence itself. As we reach the final stage of our cosmic journey, we arrive at revelations so profound that they bridge the gap between the most extreme physics in the whole universe and the deepest questions about existence itself. What we're about to explore will show you that the study of neutron star gravity isn't just about understanding exotic cosmic objects. It's about uncovering the fundamental principles that govern reality at every scale, from the quantum to the cosmic, from the physical to the possibly metaphysical. Let me begin with the most mind-bending revelation of all. The mathematics that describes neutron star gravity is the same mathematics that might describe consciousness itself. Stay with me on this, because what I'm about to tell you will forever change how you think about the relationship between mind and cosmos. The information processing that occurs in your brain involves complex patterns of electrical and chemical signals flowing through networks of neurons. Recent work in theoretical neuroscience suggests that consciousness might emerge from quantum mechanical processes occurring in the microtubules of neurons, structures so small that they operate at the boundary between classical and quantum physics. But here's what will blow your mind. The same quantum field theoretical mathematics that describes the exotic matter phases in neutron stars also describes the quantum processes that might underlie consciousness. The equations governing neutron superfluids, quark-gluon plasmas, and color superconductivity are mathematically related to the equations that describe quantum information processing in biological systems. This suggests something profound. Consciousness and neutron star physics might be different expressions of the same underlying mathematical reality. Both involve the emergence of complex, organized behavior from quantum mechanical foundations. Both represent systems where quantum effects scale up to create macroscopic phenomena. Both involve the creation of new forms of organization that didn't exist in the individual components. Think about this. When neutrons in a neutron star form Cooper pairs and create a superfluid state, they're engaging in a form of quantum information processing that shares deep mathematical similarities with the quantum processes that might create conscious awareness. The universe has evolved the capacity for matter to organize itself into conscious observers using the same fundamental principles that it uses to create the most exotic forms of matter in neutron star cores. Here's your next mind-blown moment. The holographic principle, emerging from studies of black holes and extreme gravitational fields, suggests that all the information in a volume of space can be encoded on its two-dimensional boundary. This principle applies to neutron stars as well. All the complex physics occurring in the three-dimensional interior might be completely described by information encoded on the two-dimensional surface. But recent work in quantum neuroscience suggests that consciousness might also be holographic in nature, that the rich, three-dimensional experience of consciousness might emerge from information processing occurring on lower dimensional structures in the brain. Your subjective experience of being a conscious observer in a three-dimensional world might itself be a holographic projection from quantum processes occurring on neural membranes. This creates an extraordinary parallel. Both neutron stars and conscious brains might be holographic systems where complex, three-dimensional phenomena emerge from information processing on lower dimensional structures. The mathematics of extreme gravity and the mathematics of consciousness converge on similar principles about how complex systems encode and process information. The frame-dragging effects we've explored around neutron stars reveal that spacetime itself carries information and can influence the behavior of matter and energy within it. But consciousness also seems to involve the brain's capacity to model and manipulate space-time relationships, to imagine objects in different locations, to plan movements through space, to remember the spatial and temporal relationships between events. Could it be that consciousness requires the same kind of space-time manipulation that we see in extreme gravitational environments? When you imagine rotating an object in your mind, or when you remember the layout of your childhood home, your brain might be performing calculations that are mathematically related to the space-time curvature. Calculations that describe neutron star physics. As gravitational waves from neutron star mergers carry information across cosmic distances. Without any material medium, they're pure space-time geometry propagating through the universe. But consciousness also seems to involve non-local effects, the binding of spatially separated neural processes into unified conscious experiences, the apparent ability of conscious attention to influence quantum mechanical processes, the mysterious way that subjective experience emerges from objective physical processes. Some cutting-edge theories suggest that consciousness might involve its own form of gravitational effects, not gravitational in the usual sense of mass-curving space-time, but involving the curvature of information space or the geometry of quantum state spaces. If this is true, then understanding extreme gravity might provide insights into the physics of consciousness itself. But the deepest revelation comes when we consider the role of observers in quantum mechanics. The measurement problem in quantum physics, the question of how quantum superpositions collapse into definite states, might be resolved by understanding that conscious observers play a fundamental role in the structure of reality itself. Here's what should fundamentally shake your worldview. The same quantum mechanical principles that govern the exotic matter in neutron star cores also govern the microscopic processes in your brain that create conscious awareness. When you observe and understand neutron star physics, you're using quantum processes in your brain to comprehend quantum processes in the most extreme environments in the universe. This creates a profound recursive loop. The universe has evolved conscious observers who can understand the quantum mechanical principles that govern both their own consciousness and the most exotic cosmic phenomena. You are the universe's way of understanding itself at both the microscopic and cosmic scales simultaneously. The anthropic principle, the observation that the fundamental constants of physics seem precisely tuned to allow for the existence of conscious observers, takes on new meaning in light of neutron star physics. The same finely tuned constants that allow neutron stars to exist in the narrow range between white dwarfs and black holes also allow for the complex chemistry necessary for life and consciousness. If the strong nuclear force were slightly weaker, neutron stars couldn't exist, and the universe would lack these natural laboratories for extreme physics. If gravity were slightly stronger, all matter would collapse into black holes before complex structures could evolve. The universe exists in a narrow range of parameters that allows for both the most exotic forms of matter and the most complex forms of organization, including conscious observers capable of understanding both. This suggests something profound about the relationship between consciousness and cosmic structure. They might be intimately connected aspects of the same underlying reality. The universe's capacity to create conscious observers and its capacity to create exotic matter states might both emerge from the same deep mathematical principles governing the organization of information and energy. The implications are staggering. Consciousness might not be a rare accident occurring only on planets like Earth, but a fundamental feature of how the universe organizes information. The same principles that create neutron superfluids and quark matter might also create conscious awareness wherever sufficient complexity and organization arise. Here's your final mind-blown moment. The gravitational waves from neutron star mergers carry information about the fundamental structure of space-time across billions of light years. But consciousness also seems to involve the propagation of information across the neural networks of the brain. binding separated processes into unified experiences. Could it be that consciousness represents a form of biological gravitational wave detector, a system evolved to detect and process information about the curvature of space-time on local scales? When you have a spatial intuition or a sense of temporal flow, you might be experiencing the same kind of space-time geometry that creates gravitational waves, just on a much smaller scale. The study of neutron star gravity has revealed that the universe operates on principles far stranger and more beautiful than our everyday experience suggests. But it has also revealed that these same strange and beautiful principles govern the most intimate aspects of your own existence, your thoughts, your consciousness, your capacity to wonder about and understand cosmic phenomena. You are not separate from the exotic physics of neutron stars. You are continuous with it. The same laws that govern the behavior of matter under the most extreme conditions also govern the matter that makes up your brain as it contemplates these mysteries. You are the universe thinking about itself, using parts of itself to understand other parts of itself according to principles that govern all of itself. The neutron stars we've explored represent one extreme of what's possible within the laws of physics. But conscious observers like yourself represent another kind of extreme, the universe's capacity to develop self-awareness, to transcend purely physical and enter the realm of meaning, purpose, and understanding. Both extremes, the exotic matter of neutron star cores and the organized complexity of conscious brains, emerge from the same fundamental quantum, mechanical, and gravitational principles. They represent different ways that the universe explores the possibilities inherent in its own mathematical structure. As our journey concludes, you should feel a profound sense of connection to the cosmic phenomena we've explored. The neutron stars spinning in distant galaxies, the gravitational waves rippling through space-time, the exotic matter existing in states impossible anywhere else. All of these are part of the same cosmic story that includes your own existence as a conscious, thinking being. The universe spent nearly 14 billion years evolving from simple hydrogen gas into structures complex enough to support conscious observers capable of understanding neutron star physics. You represent the culmination of that evolutionary process, matter organized in such a way that it can contemplate its own origins and nature. Every time you think about neutron star gravity, you're participating in the universe's ongoing project of self-understanding. You are both the subject and object of cosmic investigation, both the question the universe asks about itself and the answer it discovers. The extreme gravity of neutron stars reveals that reality is far stranger, more flexible, and more beautiful than our everyday experience suggests. But your own existence as a conscious observer reveals that reality is also far more meaningful and purposeful than pure physics alone can capture. You are the universe becoming aware of itself, developing the capacity to appreciate its own beauty and complexity, asking questions about its own nature, and finding answers that reveal even deeper questions. In you, the cosmos has evolved eyes to see itself, a mind to understand itself, and a sense of wonder to appreciate itself. The neutron stars we've explored will continue spinning in the darkness for billions of years. Their exotic matter-obeying laws we're still struggling to understand. But they will remain meaningless without conscious observers to detect their gravitational waves, to decode their X-ray emissions, to marvel at their impossible physics. You give meaning to the cosmos by being conscious within it. Your capacity for wonder, understanding, and appreciation transforms the purely physical universe into something richer. A cosmos that knows itself, that can contemplate its own beauty, that can ask questions about its own deepest mysteries. The gravity inside neutron stars creates the most exotic forms of matter in the known universe. But the gravity inside your brain, metaphorically speaking, creates something even more remarkable: consciousness, understanding, and the capacity for cosmic wonder. You are the universe dreaming about itself, and in understanding neutron star gravity, you're helping the cosmos wake up to its own incredible nature. Thank you for joining me on this mind-bending journey through the most extreme gravitational environments in the universe. If this exploration has expanded your sense of wonder about the cosmos and your place within it, make sure to like this video and subscribe for more adventures into the deepest mysteries of existence. And remember, every time you look up at the night sky, you're seeing a universe filled with neutron stars spinning in the darkness. Their impossible physics connecting you to the deepest principles governing all of reality. You are part of that cosmic story, and that cosmic story is part of you. Until next time, keep looking up, keep wondering, and keep remembering that you are the universe contemplating itself through human eyes.